So good afternoon everyone. So for this moment, since nabanggit ko rin po last time na itong June natin ay medyo maano yung schedule natin, hectic ang schedule natin for so many reasons and for so many activities sa ating school. So to make up for that, sisimulan ko na po mag-upload ng mga synchronous sessions natin para sa ating subject. Okay? Para at least hindi kayo para at least ma-cover pa rin po natin yung mga prescribed topics na naiset ko po sa ating syllabus. So for this moment, we're going to have the discussion regarding cosmology. So this is a topic na kung saan magkaduktong yung modern physics na subject natin at yung astronomy na subject natin. So either way, itong topic na to ay hindi ko na uulitin sa subject natin na astronomy because this one is intended for the subject ng modern physics natin. Okay? So without further ado, let's just give me 1 minute to share my screen with you. So yan, hopefully naka-flash na sa ating screen yung aking presentation. So again, magandang araw sa aking mga estudyante mula sa BSED3S. And for our subject modern physics, this would be our topic for week 12, lesson number 7, which is all about cosmology. So again, sabi ko nga po, this is a merger between our subjects na modern physics at astronomy. So some of the topics here will be tackled also sa astronomy subject natin, but this one will be concerning more on the particles na na-discuss din natin last time sa subject na modern physics. So the topic outline for this session will be galaxies and birth of the universe. So this one, marami tayong mga incorporate na mga topics and I hope that everyone will be at least ay makasunod sa ating lesson for this afternoon. So for the first one, we are going to have galaxies. And for sure, you're familiar with the idea na tayo ay kabilang o nasa loob tayo ng tinatawag nating Milky Way galaxy. That's our home galaxy. Yan yung home base natin, kumbaga. So in this case, let's start with the definition first with cosmology. So pag sinabi natin cosmology, it's actually the study of the universe, including its properties, structure, and evolution. So pangkalahatan na ito. Okay? So titingnan natin dito, aaralin natin ano nga ba itong kalawakan na ito? Ano nga ba ang bumubuo sa kanya? Ano ang struktura nito at paano ito nag-evolve from the very beginning and probably in the future? Ano magiging itsura ng ating universe? But this lesson so far, itong lesson na itatakil natin ngayon, will be concerning mostly on the beginning and the present condition ng ating universe. We will not discuss anymore ano yung magiging future kasi most of them are hypothetical or theoretical. Okay? So tandaan natin na yung universe natin, it consists of hundreds of billions of galaxies and each galaxy contains billions of stars. So itong nakikita nating litrato na ito sa ating presentation, hide ko lang po itong mga to. Okay? Zoom lang natin. Each of the points here sa ating diagram, they are all galaxies. So hindi sila mga stars. So itong mga tuldok-tuldok na to, even this bright one, they are all examples of galaxies. And each galaxy contains billions upon billions of stars. So imagine the number of galaxies present sa picture na ito. This is just one portion of our sky. Okay? So the model that most accurately describes the birth and current state of the universe is called the Big Bang Theory. Okay? According to this model, the universe began about 13.7 billion years ago in a cataclysmic explosion and then it continued to expand and cool and evolve to its current state. So ganyan na po katanda yung ating universe. It's based from this theory, 13.7 billion years ago old na po yung ating universe. Ang ating daigdig o yung solar system natin ay nabuo 4.5 billion years ago lang. So later addition na lang tayo sa ating universe. So napakatanda na ng ating universe, 13.7 billion years ago, and it started with a bang. Hence the name, Big Bang Theory nga eh. Okay? So this is our timeline of the evolution of the universe. So as you can see here sa ating diagram, we started with Big Bang. By the way, itong ating discussion is more on theoretical. Ito yung sabihin natin, yung pinaka-pinaniniwalaang theory na nagpapaliwanag ng pagsisimula ng ating universe. So after that one, about a million years ago, and then 400 to 500 million years, we have started to create the first galaxies and stars. And from that point, nag-evolve na po yung ating galaxy. And from about 9.5, 9.1 billion years or 4.6 billion years ago, nagsimula na ang mabuo ang ating solar system. And right now, at present day, we are now 13.7 billion years old na po yung ating universe. Okay? So titingnan natin later paano na-compute, paano nila nalaman na 13.7 billion years nga yung ating universe. So pag sinabi natin galaxies, these are collections of interstellar matter, stars, and stellar remnants that are gravitationally bound. Yung mga findings ngayon actually guys, is actually most of the galaxies, especially mga spiral galaxies and elliptical galaxies, ay meron mga supermassive black hole. And this supermassive black hole, sila po yung parang nagiging bridge para mapagdugtong this creates the pulling force para mapagsama-sama natin yung mga materials ng ating galaxy from the interstellar matter, from the stars, and even stellar remnants. So sa gitna ng mga galaxies natin, especially the large one, they have supermassive black hole. Recently, I think last year lang, nakuhanan natin o nagkaroon tayo ng composite picture ng Sagittarius A star, and this is the supermassive black hole na makikita sa gitna ng ating Milky Way galaxy. Recent observational data indicate that supermassive black holes may exist at the center of most galaxies. And aside from that one, aside from the presence of this supermassive black holes, we can also have spherical halos of very tenuous gas and numerous star cluster or globular clusters, especially sa mga malalaking galaxies natin. So here is a typical galaxy. As you can see here, that one is an example of a spiral galaxy. They have arms, a central bulge, and the halo that is composed of globular clusters. So just like what I have mentioned, ito yung picture na I think this is the same picture earlier. Sabi ko nga po, this is just a tiny sliver of the sky natin. So yung napakaraming tuldok na yan, ito lang po siya. Ganyan lang po kalit yan. This is north of the constellation of Ursa Major. Okay? So this is small box, zoom natin, ito po yung makikita dyan, itong mga dots na to. And each dots here are not stars. These are collection of stars called galaxies. Imagine the number of galaxies present now sa ating universe. Okay? This was taken by the Hubble Deep Field, a feature of the Hubble Space Telescope, for a period of 10 days exposure. Okay? So ganyan kadaming galaxies ang nakikita natin in a very small portion of our sky. So the Milky Way galaxy is a spiral galaxy consisting of a thin disk about 100,000 light years in diameter with a central bulge. So tingnan natin gamit tayo ng laser. This is the central bulge and this is the thin disk ng ating galaxy. And a spherical region called halo. So surrounding our galaxy, meron tayong spherical, yung perimeter natin, that is actually called the halo, that surrounds the entire disk. The disk contains most of the gas and dust of the interstellar medium. So ibig sabihin, yung mga materials na present sa ating galaxy, dyan matatagpuan sa ating disk ng ating galaxy. While the halo contains only a small amount of hot gas and virtually no cold gas. Ano po yun? Wala po yata dyan, ma'am. Sige po, ma'am. Okay lang po. Okay, going back to our discussion. So, the thin disk of our Milky Way galaxy contains most of the gas. So, nandyan yung bulk ng bigat ng ating galaxy. And the halo surrounding our galaxy, halos wala ng gas doon. Medyo konting materials na lang nandyan and virtually very few materials. Nandyan po matatagpuan yung mga globular clusters. So, if you're going to zoom in sa ating slide, let me use the zoom feature here. Ayan. So, this is our central bulge. This is the disk. Since our Milky Way is a spiral galaxy, meron siyang spiral arms. And surrounding our galaxy, we have our globular clusters. Okay? So, yung next picture naman here, we have, ito side view yan. So, it's an edge-on schematic view of the Milky Way. You can see there the bulge. Okay? Yung gitnang portion, yung nandyan sa gitna na yung sinasabi nga nating supermassive black hole. We also have the sun's location at around 27,000 light years away from the center of our galaxy. And the thickness or yung kapal ng ating disk ng ating ng ating universe, ng ating Milky Way is 1,000 light years lamang compared to the bulge ng ating Milky Way. And surrounding the bulge, surrounding the disk ng ating Milky Way, you can see there the halo, which is mainly composed of globular clusters na i-discuss natin sa astronomy na subject natin. Moving on. So here are some examples of our galaxies, mga malalaking galaxies yan. And this one are spiral galaxies. Okay? The first one is NGC 6744. New General Catalog po yan ng, it's a spiral galaxy very similar to our Milky Way. So kitang-kita natin yung bulge. Baka nasa ano po, nasa crystal line sa management department. Ay, ako na po. Okay lang po. Yes. Okay lang po. Sige, mamaya iabot. So for the next picture naman natin, we have NGC 4414. It's also a spiral galaxy na yung tilt niya is tilted to our line of sight. Kaya kitang-kita natin yung structure ng yung kanyang halo, yung kanyang bulge niya, yung disk ng ating galaxy na yan. And we also have here a picture, the third picture here, we have NGC 891. It's a spiral galaxy seen edge on. So parang side view ang nakita natin. So kitang-kita natin, let me draw para kitang-kita natin sa ating diagram na nandito yung bulge niya. And probably this one, ito yung halo niya. Nandyan yan. And this is our thin disk. Ito naman, medyo naka-slightly angle. Ito naman top view, kumbaga, ng ating galaxy. So ganito ang, halos ganito ang itsura ng ating Milky Way galaxy. So here's another picture of our another galaxy. This one is called the Sombrero Galaxy. Kaya siya tinawag na Sombrero Galaxy kasi mukha siya yung sombrero ng mga Mexican, yung talaga nakaumbok tas may malapad na rim. So that is NGC 4594. That's a spiral galaxy with a very large bulge. Kitang-kita man natin yung bulge ng ating galaxy dito. And the halo surrounds the entire galaxy. So sa totoo lang, guys, yung mga parang mga dots na makikita natin surrounding the galaxy, this is the halo of the galaxy, and this may contain the what do we call this? The globular clusters. This image shows a region of the galaxy about 82,000 light years across. Yung last picture natin sa slide na ito, we have naman yung central part of NGC 2787. It's a lenticular galaxy. It's also a spiral galaxy pero medyo a little bit unique yung kanyang orientation. Kaya ganyan po yung itsura ng kanyang ng galaxy. And aside from that one, wala siyang obvious or noticeable spiral arms. So wala siya ng arms na typical nakita sa mga spiral galaxies natin. So the disk population na matatagpuan natin sa flat disk includes stars of all ages and masses that orbit the disk of the galaxies. So kung susumahin natin yung ating sun ay kabilang sa disk population kasi nandun tayo eh. Nandun tayo sa disk ng ating Milky Way. Yung another group naman ng mga population ng stars ay tinatawag naman nating spheroidal population. Spheroidal kasi itong mga stars na ito ay matatagpuan sa bulge at sa halo. So ibig sabihin kung tutusin itong mga stars na matatagpuan dito sa disk na yan, these are called the disk population stars. And the one that's surrounding or within our bulge or within the surrounding halo ay tinatawag naman nating spheroidal population. So let's move on naman. Yung elliptical galaxies naman, they only have the spheroidal component. Wala siya ng disk component niyan. So halos yung bulge na lang ang makikita natin sa ganitong klase ng galaxies. That is, elliptical galaxies look like much of the bulge and halo of the spiral galaxy. Wala yung disk. So kanina sa spiral, kita natin yung disk, kita natin yung bulge. Sa elliptical galaxies, hindi na natin or totally absent yung disk component niya, and ang present na lang po ay yung spheroidal component. Hence, the shape is circular or elongated like this one. So wala yung typical na nakikita natin sa spiral galaxy na may mga arms. Wala yan. Ang meron lang sa kanya is yung spheroidal component ng ating galaxy. Elliptical galaxies usually contain very little little dust or cool gas. Although some have relatively small and cold gaseous disks rotating at their centers, However, some giant elliptical galaxies contain substantial amounts of very hot gas. Sa totoo lang, hindi bukod sa mga presence ng mga hot gas na yan, no, evidence sa core ng ating galaxy, yung mga elliptical galaxies na yan, they are also supermassive. Sobrang lalaki. So kung ito yung M87 natin sa very large galaxy, it's even larger than our galaxy, sa Milky Way galaxy, it will dwarf the Milky Way galaxy that we know. So ibig sabihin yung supermassive black hole na meron kay M87 is also very large. Imagine that one. Itong region na ito, itong nakikita nating spherical structure na yan, that's 300,000 light years across. Ganyan kalaki yung mga elliptical galaxies natin. And the third group ng ating mga galaxies ay tinatawag natin mga irregular galaxies. They are in miscellaneous class, so very random yung mga shapes nila, very peculiar yung mga shapes nila. Hindi sila nagko-conform sa tinatawag nating mga elliptical galaxies and spiral galaxies. The best example ng ating mga irregular galaxies ay yung closest irregular galaxy natin na Magellanic Clouds, yung Large and Small Magellanic Cloud. Unfortunately, since this is very far away from, nasa southern hemisphere makikita yan, hindi visible sa ating bansa yung Magellanic Clouds na yan. So, kinakain siya ng light pollution kaya hindi na siya visible. So, we have here a picture of Large Magellanic Cloud and Small Magellanic Cloud. We also have here NGC 1313, an irregular galaxy with scattered patches of star formation. Okay? Maliliit sila kasi some of them are just remnants ng collision ng mga galaxies, or maaring napatalsik lang sila, mga dating bahagi sila ng spiral galaxy na natanggal, na detach, kaya very irregular yung shape nila. Unlike the mas defined na shape ng spiral galaxies and elliptical galaxies. So in this case, Edwin Hubble, he's a very famous astronomer. He invented a system for classifying galaxies that organizes the galaxy types into diagram shape like a tuning fork. So ito po yung tuning fork diagram ni Edwin Hubble. If you have E sa unahan, ibig sabihin elliptical ka. Okay? And ang rule dito is once you go nearer sa zero, mas nagiging circular yung structure natin. So check lang natin kung baka hindi na ako naririnig ng ating discussion. Check lang natin yung audio. Yan. So again, pag ang number ay mas malapit sa zero, mas circular yung elliptical galaxies natin. And if you have a larger number, example here is 5, mas elliptical siya, mas flattened yung shape niya. Sa mga spiral galaxies naman natin, we have some examples of shapes ng galaxies natin. Meron tayong mas defined na galaxy here. We also have a barred spiral, mga ganyan. So kitang-kita natin na may mga bars yung ating spiral galaxies. So, yan yung device ni Edwin Hubble para ma-distinguish or ma-characterize natin yung iba't ibang uri ng galaxies from the elliptical to our spiral galaxies. Yung irregular galaxies natin, hindi siya kasama dito since they have different shapes. Hindi uniform yung shape ng ating mga irregular galaxies. So, in this case, yung ating mga spiral galaxies, pag nagsama-sama sila in a very loose collection, they will be called groups. So yung tayong Milky Way, yung Andromeda Galaxy at Triangulum Galaxy, we are the largest member of what we call the local group of galaxies. So magkakatabi tayo kumbaga, kung sa astronomical scale, we are close to each other. Kaya lang 2 billion light years away ang Andromeda Galaxy. Sobrang layo din yan sa totoo lang. Pag naman nagsama-sama yung ating mga elliptical galaxies in a group, ang tawag naman doon ay cluster of galaxy. And sa totoo lang, tayo ay kabilang sa tinatawag nating Virgo cluster of galaxies. Okay? Kasi yung sa Virgo cluster, kaya siya tinawag na cluster kasi nga most of the members of this cluster are elliptical galaxies. Tayo ay maliit na bahagi lamang ng Virgo cluster of galaxies. And they may extend for almost 10 million light years. Imagine the distance, 10 million light years ang layo ng ating mga components ng mga clusters and groups natin. So this one, itong figure na ito, pinapakita natin dito isang tinatawag nating Hickson compact group. Compact group or group in this case kasi kitang-kita natin na tatlo kagad ang spiral. 1, 2, 3. So most probably this one is spherical or elliptical in this case. Kaya siya tinawag na group. So here's another picture. We have Abel 1689. It's a cluster. So ibig sabihin most of the members of our galaxy of our groups of galaxies here are elliptical. Kitang-kita naman natin. Ilan lang dyan yung spiral. Isa, dalawa, tatlo. Mga whitish yung spiral natin. But the rest are yellowish and they are all elliptical galaxies. Ito naman yung pinapakita nating local group of galaxies natin. So yung local group of galaxies natin, in this case, ating diagram yung nasa center natin is Milky Way galaxy. And the two larger components din ng ating local group ay yung ating Andromeda galaxy and M33, yung Triangulum galaxy. So yan yung big components ng ating local group. So, ang tanong ngayon dito guys is paano natin ma-measure? Alam naman natin na nababanggit ko mga numbers is billion of light years, millions of light years. So, ang question dito is paano natin na-measure yung ganyang mga large distances? Okay? So, sa astronomy, we are going to use chains of methods para ma-measure natin yung iba't ibang sukat na yun, yung iba't ibang distansya na yan. So, here is a diagram showing you the methods that we can use to measure distances. So for example, if we have a distance between 1 AU to 100 parsecs, we are just going to use radar ranging, stellar parallax, and spectroscopic parallax. Pero pag lumalayo na yung ating galaxies, we are going to use another method like variable stars, Cepheid variables, and even other standard candles. So by the way, ang tawag sa mga ganito, itong mga panukat na ito ay standard candles because we can use this one as our, sabi natin, basis to measure large distances sa ating universe. So ang i-discuss ko lang ngayon is yung tatlong uri ng standard candles natin, yung main sequence stars, Cepheid variables, and distance standard candles. So yan, nakita natin sa ating inverted pyramid na ito. It shows, pinapakita lang dito yung ating mga techniques na pwedeng gamitin ng mga astronomers to measure long distances. Okay? So here we have parallax. Unfortunately, yung subject na to, yung modern physics, ituturo ko tong stellar parallax sa subject nating astronomy. So kayo rin nga pala estudyante ko dun. Anyway, so ituturo ko yung pag-compute ng stellar parallax dun sa astronomy subject natin. But in this case, to give you an idea, yung stellar parallax is kinocompute natin yung, sabihin natin, apparent shift ng paggalaw ng ating planeta. You can try this one at home. For example, i-extend nyo yung kamay nyo sa harap ng mata ninyo. You just open your eyes, yung kanang mata lang. After 5 seconds, i-close mo yung right eye, buksan mo yung, i-open mo yung kaliwang mata mo, mapapansin mo parang gumagalaw yung ating daliri na nasa harapan ng mata natin. And parang ganyan din po ang nangyayari sa ating mga stars if you're going to measure stellar parallax. Okay? So we're just going to have 2 points sa orbit ng ating planeta around the sun, and we're just going to measure kung gaano kalaking movement. Sa totoo lang, maliit na movement lang yan guys, hindi siya gaano kalaki. So they're just going to calculate or measure the movement na yan, yung distance na yan. And we are now going to have the stellar parallax. Kaya ito sa mga malalapit na stars. Pero syempre, habang lumalayo tayo, mas lumiliit yung stellar parallax na yan, and it becomes inconvenient ng gamitin. So applicable lang ito sa malalapit na stars. Yung next naman natin, we have main sequence fitting. Ginagamit naman natin ito para ma-measure din yung mga distances na yan. Ang goal naman natin dito sa main sequence fitting is that we have bunch of stars na alam natin yung distansya. Alam natin yung brightness and distance. For example, yung Hyades. Yung Hyades, it's a group of stars in the constellation of Taurus. Alam natin yung liwanag nila. In this case, nasa y-axis natin. At alam din natin yung temperature, yung init, yung surface temperature ng stars na yan. And we're just going to compare that one sa isa pang grupo ng star cluster, which is in this case Pleiades. So in this case ating diagram na ito, si Hyades, the main sequence of the Hyades is 7.5 times as bright as that of the Pleiades. Kaya lumalabas din na mas malayo si Pleiades in this case. So may mga computation na ginagawa yung mga astronomers natin to determine if that star cluster or group of star is farther from us dito sa ating planeta. Okay? So ito mas malaking, ito pala may mas malaking picture pala ng main sequence fitting. So as you can see here, meron tayong ni-note na star dito sa Hyades star group, cluster of stars. We have the main sequence of the Hyades. Pag sinabi natin main sequence, ito yung parang teenager ng mga stars natin. So yung sun natin is an example of main sequence. So if we have a standard, for example, one star from this group at alam natin yung liwanag niya, alam natin yung distansya niya, and even the surface temperature, we can use that standard to compare at makuha rin natin yung distansya ng iba pang mga star clusters. So, more on math. Ang mahalaga lang dito is alam natin na scientists or astronomers also use comparison to determine the distances between different objects sa ating galaxy. Next naman, Cepheid variable. This one is it's actually cool kasi very few na mga babae ang nag-venture sa astronomy. And we have here Henrietta Leavitt, and she discovered the periods of Cepheids. So, yung Cepheids na ito. Itong Cepheid variables, these are stars na kung saan pabago-bago ang liwanag niya. Minsan lumiliwanag siya, minsan dumidilim siya. And scientists can actually plot yung changes na yan, yung dimness and brightness ng ating mga Cepheid variables. And in this case, magagamit natin actually yung pagbabago-bago ng characteristics ng Cepheid variables na yan to measure distances. So if you're going to zoom here, zoom natin. So, meron tinatawag tayong Cepheid period luminosity relation. Yung period, syempre, yung araw kung saan lumiliwanag, lumalabo, dumidilim, yung ating stars. And on the y-axis, we have luminosity in comparison with our sun. So, the data show that all Cepheids of a particular period have a very nearly the same luminosity. So, yun ang nakitang relationship ni Henrietta Leavitt sa kanyang data. Na yung ating mga Cepheid variables, they have nearly same period and same luminosity. Magkasing rami sila ng energy na inipoproject sa ating galaxy. So, escape, data lang natin ulit. So, measuring a Cepheid's period therefore allows us to determine its luminosity and calculate its distance. Kasi dyan magagaling ang ating mga astronomers since we cannot, tayo pwedeng lumapit sa mga stars, hindi natin pwedeng puntahan yung mga stars na yan. So, pwede tayong gumamit ng mathematical models to determine its distance. So, pag alam natin yung luminosity, alam din natin yung distance. So, ngayon, yung mga scientists natin, mga astronomers natin, they are now looking for Cepheid variables sa mga malalayong galaxies. Kasi pag alam nilang Cepheid variables yan, makukompute nila yung distance niyan. Okay? And lastly, sa ating mga groups ng measuring or yung measurement na ginagamit, pwede tayong gumamit ng another standard candles using supernova. Okay? Right now, nagkaroon ng supernova sa Pinwheel Galaxy. Hopefully, magkaroon na ng time at gumanda rin yung panahon, guys, kasi medyo dim yung galaxy na ito at hopefully makita ko may supernova at kung totoo nga visible yan through small telescopes. But anyways, ang ginagamit nila dito is that they use supernova to measure the distances ng ating galaxies. Okay? So here's a picture of a white dwarf supernova near peak brightness. So ngayon, since alam na natin na pwede palang sukatin ng ating mga astronomers yung distances, yung mga large distances sa ating universe, sa ating galaxy. So, sino nagsimula? Sino nagsimula magsukat ng mga distances na ito? So in this case, ito yung nabanggit natin kaninang scientist, Edwin Hubble. Sabi ko nga, he's a famous astronomer. He's actually the one who devised the way kung paano natin makakategorize yung iba't ibang galaxies natin. But he is more famous dahil sa kanyang pagkakadiscover na yung ating universe ay nag-expand. So tingnan natin muna to. So using the largest telescope in the world at the time, this one is from Mount Wilson at Los Angeles, California, Hubble identified individual Cepheids. So ibig sabihin during that time, ginagamit na nila ang Cepheid variables para makapag-measure ng distances, large distances. And aside from that one, this one enabled him to determine their luminosities and eventually their distances kasi may relasyon nga yung period at luminosity. So ngayon, anong lumalabas sa una niyang observation? Na yung Andromeda Galaxy na akala natin daw nung mga unang panahon na kabilang sa Milky Way ay masyadong malayo para maging bahagi ng Milky Way Galaxy. Okay, so that's the first finding. Sabi ni Edwin Hubble, parang hindi sapat na ito lang ang titingnan ko. Parang pwede ko rin i-observe yung iba't iba pang mga galaxies. So, anong nangyari dito, ito yung data na nakuha ni Edwin Hubble. So sabi niya, hindi sapat ni si Andromeda Galaxy. Ang ginawa niya, inaral din niya yung mga Cepheid variables sa iba't ibang mga galaxies pa. At anong na-discover niya? Nag-expand si universe. So lumalapad yung ating universe. So, kung lumalapad yung universe natin, kung magkakaroon tayo ng time machine, pwede tayong bumalik sa time na kung saan hindi nag-expand, o I mean, on the smallest size pa yung universe natin. So ito yung birth ng Big Bang Theory na sa ngayon alam natin na ito yung sinasabing pagsisimula nga ng universe natin. So ito yung mga measurements, I mean mga techniques na ginagamit ng astronomers natin uh, to measure distances sa ating galaxy. So using the idea na nagamit nga na nabanggit ni Edwin Hubble na nag-expand sa universe, meron tayong tinatawag na cosmological principle. Tingnan natin kung ano itong cosmological principle. On very large scales, the distribution of galaxies appear to be relatively smooth. So, parang at any point, kahit saan ka magtumingin, feeling natin smooth, very uniform yung distribution ng mga galaxies natin sa ating universe. So meaning that the overall appearance of universe around you would look more or less the same no matter where you are located. So kahit saan ka magtumingin sa ating universe, very smooth, very uniform ang distribution ng galaxies. So this gives us the idea na yung matter in the universe are evenly distributed without a center or an edge, or which we now call as the cosmological principle. So yung cosmological principle na to, pinapakita lang nito yung distribution ng materials sa ating universe. Okay? But, okay, it does not explain yung nakita nga ni Hubble na nag-expand sa universe. Okay? Although the universe as a whole is expanding, individual galaxies and galaxy clusters do not expand. Kasi best example ito, sa mga magtuturo sa senior high school, kasi this is a topic in senior high school, pwede kayong gumamit ng simulation or analogy. Dala kayo ng lobo, tapos magdikit kayo ng mga spiral shape o mga parang galaxy na icon or logo, dikit nyo sa logo na yan, tapos hipan ninyo. And your students will notice na lumalaki yung distansya sa pagitan ng mga galaxies, pero yung galaxy hindi naman lumalaki. Okay, so yun, pwede nyo i-try yan sa mga estudyante ninyo once you're going to discuss the topic about the expansion of the universe. So lobo, then magdikit yata ang ginagawa nila is nagdo-drawing sila ng galaxy mismo sa lobo. Eh, ang mangyayari kapag nag-drawing tayo sa lobo, lumalaki din drawing. So it violates the observation na nakikita natin sa ating galaxy. So better na magdikit na lang kayo ng picture ng galaxies. Okay? So distances between galaxies are always changing because of the expansion of the universe. Okay? So every minute, every second, lumalapad yung ating universe. Okay? And our scientists, our astronomers are trying their best to account these changes. So it's therefore best to express the distance to a faraway galaxy in terms of its look-back time. So this one, na-discuss na natin to last time sa space-time diagram na nag-discuss tayo ng general theory of relativity. So hindi ko na siya masyadong i-ano pa, pero this figure will just show us na nag-expand yung ating universe. Okay? So this is a space-time diagram, and this is the location of the Milky Way galaxy, and we have here mga galaxies surrounding us. Okay? And on the x-axis, we have the distance from the Milky Way, and on the y-axis, we have time. So as you can see there, na as time progresses, lumalayo yung ating mga objects o yung mga malalapit na objects sa atin since our universe is expanding. We can measure the distance, we can measure the time it takes para makapag-travel yung mga light particles na yan from one galaxy to the original position natin. So makikita natin, the astronomers are very good in math. They can calculate, they can compute kung gaano kalaki na ang ini-expand ng ating universe. Okay? So the expansion of the universe during that time stretches the light coming from the galaxy, leading to what we call cosmological redshift. Ibig sabihin, lumalayo yung ating mga objects sa atin. So, sabi ko nga kanina, kung lumalapad ang ating galaxy, there should be a point na kung saan nananatili tayong small point. And dito tayo papasok sa second half ng ating discussion, which is all about birth of the universe. So at least marirelate natin discussion natin last time tungkol sa mga particles. Okay? So nung baby pa yung universe natin, on the early universe, our early universe was filled with radiation and elementary particles. So yung elementary particles na yan, yung mga na-discuss natin, mga electrons, protons, neutrons, quarks, leptons, baryons, at kung ano na pang mga particles na yan. So wala pa tayong mga atoms nung unang panahon. They're just particles. So it was so hot and dense that the energy radiation could turn into particles of matter and antimatter, which we all know na every time na mag-meet si antiparticle at yung particle niya, they will undergo particle annihilation. And once na nag-annihilate na sila, nasira sila pareho, dahil nga sa conservation of energy, they will just turn back into radiation. So parang ganyan yung naging sequence sa early universe natin. One particle will be, the particle and the antiparticle will annihilate each other, and the annihilation will produce energy. And that energy will, in turn, magbubuo ulit ng particle and antiparticle, and paulit-ulit lang po yan sa early universe natin. Ganyan yung ganap nung unang panahon sa early universe natin. But please take note that these are just hypothetical or theoretical. Siyempre, hindi naman tayo makakabalik sa unang panahon, hindi naman tayo makakabalik sa early days ng universe natin. So these are just, sabihin natin na best guess ng ating mga scientists kung paano nagsimula yung ating universe. Sa totoo lang, pag nag-discuss kayo sa senior high school nito, you will also discuss the other theories. May mga, I think meron pa sa mga philosophers natin, i-discuss nyo yung mga views nila, mga perspective nila sa early days ng universe. Pero dito sa ating discussion, since we are dealing with modern physics, we are just going to deal with Big Bang Theory lang. Okay? So during the early days ng ating universe, yung apat na distinct forces na na-discuss natin last time, yung strong force, electromagnetism, weak force, and gravity, halos pareho sila. Okay? They are united at one point, okay, na tinatawag nating super force. Yes, it might sound weird or medyo sci-fi kasi more on theory talaga ito. So nung early days ng ating universe, it's 10 raised to negative 43 seconds, ibig sabihin 10 na sinusundan ng 43 na zeros. Okay? So, during that time, yung apat na force na yan, they are all united or pare-pareho lang sila. Okay? So, current model of fundamental physics predict that they are just different aspects of smaller numbers of more fundamental forces. So, parang nagpo-fuse yung iba't ibang forces as we go back in time. So, these models predict that the four forces would have been merged together at the high temperatures and that prevailed in the early universe. So, nung baby days or early days ng ating universe, yung mga forces na yan, they are just nag-merge lang sila into one quote-unquote super force na tinatawag natin. Okay? So this super force o itong four forces na to, distinct right now. Alam natin na may gravity, alam natin na may strong force between the nucleus and the particles, alam natin na may electromagnetism, kaya nga may kuryente tayo ngayon. Pero if we go back in time, pag bumalik tayo sa early days ng universe natin, these four forces are not unique. They are not distinct from each other. They are just one force. So, i-zoom ko lang to. Ito maganda tong diagram na to kasi kaya lang hindi pala kasya. Anyways, kasya. Check natin. Yan. So we have different era. Kung sa geology, meron tayong mga Cenozoic, Jurassic period, may mga ganyan. Yung ating universe may ganito din. Mga eras. So the first era after the Big Bang is what we call the Planck era. And in this case, halos mga elementary particles lang ang meron dito. Okay? So the temperature is 10 raised to 32 Kelvin. Imagine the temperature during that time. It's 10 followed by 32 zeros. Eh yung 100 degrees Celsius nga, napapaso na tayo. What for itong 10 raised to 32 na ito. Okay? Then after that one, we have the GUT era. Okay? Or the Grand Unified Theory era, na kung saan two forces are thought to have operated during the GUT era. The gravity and the GUT force. Okay? So, during this time, at this point, the gravity become distinct from other forces. So, dalawang forces na ang present sa GUT era natin. We have gravity and the GUT force. Okay. Again, pag sinabi natin GUT, that's Grand Unified Theory. Okay? Na at this point, yung ating apat na forces, dalawa na sila ngayon, yung gravity and the GOT force. Si GOT force eventually maghihiwalay yan sa tatlong force na naiwan natin. After that one, we are followed with the electroweak era na kung saan nag-diverge ulit, balikan na natin, nag-diverge na ngayon si GOT force or GOT force and strong force. So naghiwalay na sila. Okay? The GOT force split into strong and electroweak forces, perhaps accompanied by dramatic instant expansion called inflation. Followed by this one, we have the particle era. So during this time, nagsimula ng mabuo yung mga protons natin, mga electrons natin. And na-discuss din natin last time yung ating mga protons and neutrons are made up of quarks. And yung ating electrons is also an elementary particle. So at least dito at this point, buo na yung ating mga particles. Okay? Kasi nga, meron na tayong electroweak forces o mga strong forces na ito. Then after that one, an era of nucleosynthesis. From the word itself, nucleosynthesis. Synthesis, pagbuo, nucleus. We are now starting to fuse these particles and forming the hydrogen atom. And during this time, alam naman natin na yung mga stars natin, ang main components yan ay hydrogen. And which we slowly converted into helium. Madidiscuss natin ng malaliman itong nucleosynthesis pagdating natin sa astronomy na subject natin sa tingnan kung kaya pa ng schedule later. Okay? Then after that one, since nabubuo na natin paunti-unti yung hydrogen nuclei, we are now going to move on with the era of the nucleus or the era of the nuclei. No, kung saan karamihan na o malaking bahagi na ng ating universe ay binubuo na ng mga free electrons and yung nuclei, yung atomic nuclei natin. Okay? So right now also the universe is now composed of 75% hydrogen and 25% helium by mass, the two lightest elements that we have. By the way, ito ay nangyari 5 minutes after Big Bang. Baka sabihin nyo, napakatagal nangyari itong dinidiscuss natin. Balikan lang natin, baka nagkakaanuhan lang tayo. Yung Planck era, it's 10 raised to negative 43 seconds. Parang mas mabilis pa sa isang iglap. Mula sa pagsabog pala ng Big Bang, we have the Planck era na kagad. After that one, nag-diverge, naging GOT era, nag-diverge ulit si electroweak era. Then after 5 minutes, meron na tayong mga nucleus ng hydrogen and helium. Imagine that one. Okay? So ganun kabilis ang naganap. So pagsabog pala ng Big Bang, 5 minutes after that one, may mga nucleus na tayo ng hydrogen and helium. And hanggang sa ngayon, we now have what we call the era of atoms. Since we are now the regular matter, binubuo tayo ng regular matter na meron tayo, na binubuo tayo mga tao, mga planets, mga solar systems, mga Milky Way mga galaxies natin. So neutral atoms are formed and energy are now easily available na pwede natin gamitin. And this era of atoms lasted until stars and galaxies began to form. So we are now beyond era of atoms. Nandito tayo sa eras ng galaxies, ng formation ng mga star systems, mga ganyan. Okay? So sabi nga natin kanina, the Big Bang Theory is a model of nature designed to explain a set of observations. Okay? So ito yung ginamit ng ating scientists para sagutin yung kanilang observation. They do not have the ability to go back in time nga di ba? So we are just having hypotheses or theories, kumbaga. So this model was inspired by Edwin Hubble's discovery of the universe expansion. Okay? If the universe has been expanding for billions of years, then simple physical reasoning suggests that conditions ought to have been much denser and hotter in the past. So parang yun yung common sense Kung lumalapad yung universe natin, pwede tayong bumalik sa past, sa nakalipas, na kung saan yung ating universe, it's very small, very dense, and very hot object. So it's a very small point. Everything is inside that very small point during the early days ng universe natin. Okay? So ano yung bakit nagkaroon ng traction si Big Bang Theory? Bakit siya ang napili or nagustuhan ng mga scientists natin? Dalawang dahilan. Una, it predicts the radiation na nakikita natin ngayon. Yung tinatawag nating cosmic microwave background. Okay? So, it predicts that the radiation that began to stream across the universe at the end of the era of nuclei should still be present today. Kasi sabi nga natin kanina, di ba? Every time na nagkakaroon ng particle interaction, we are now going to produce radiation. Okay? And this radiation are still present today, and Big Bang Theory can explain that. Yung dinidiscuss nating timeline kanina. We find that the universe is filled with what we call the cosmic microwave background, and it match what is expected sa ating Big Bang model. Yung isang theory naman, or rather isang reason kung bakit mas sabi natin bumenta si Big Bang Theory is that it predicts that some of the original hydrogen in the universe should have fused into helium during the era of nucleosynthesis. Which is true naman, di ba? Once na naghalo ang nuclei ng hydrogen natin, we're going to create helium nuclei. Observation of the actual helium content of the universe closely matched the amount of helium predicted by the Big Bang Theory, 75-25. Aside from that one, mayroon na tayong mga ginamit ng mga sophisticated telescopes na kaya mag-detect ng microwaves. Microwaves are electromagnetic waves between infrared and radio waves. Okay? And this cosmic microwave background, or CMB, is the radiation left over from the Big Bang. So hanggang ngayon, nadedetect pa rin natin yung radiation na yan. Its spectrum matches the characteristics expected of the radiation released at the end of the era of nuclei, spectacularly confirming a key prediction of the Big Bang Theory. Kasi kung totoo nga yung sinasabi sa Big Bang Theory, dapat may radiation pa rin hanggang ngayon. Yung radiation na nabuo during the early days ng ating universe. Okay? So itong cosmic microwave background na ito ay manifestation lamang ng mga naganap, ng mga kaganapan during the era of nuclei, during the first moments ng ating universe. So ito yung second explanation niyan. The Big Bang Theory predicts that the ratio of protons to neutrons during the era of nucleosynthesis, and from this predicts that the chemical composition of the universe should be about 75% hydrogen and 25% helium by mass, which is still countable. Naka-account pa rin natin ngayon na ganyan po yung mga carbon. Sir, paano yun? Yung carbon, hydrogen, nitrogen ganyan, it's just 0 point something percent ng totality ng material sa ating universe. It's a very small fraction lamang ng ating observable universe. Check lang natin, baka nag-error na yung audio. Medyo malakas ang ulan. Ayan. The prediction matches observations of the cosmic abundances of elements, another spectacular confirmation of the Big Bang Theory. So, ibig sabihin ito mga na-obserbahan natin ngayon, it actually naipapakita niya, it corresponds to the different events during the early days ng universe natin. Yung pagbuo ng hydrogen atom, ng helium atom natin, it corresponds to what happened 13 billion years ago na ang nakararaan. So, by next week, since nababanggit na natin paulit-ulit itong radiation, balik lang ako sa platform natin, since paulit-ulit ko na nababanggit itong radiation na to, we will be discussing next week nuclear physics. Okay? So, ito ay bagong addition sa syllabus natin kasi right now, nung nakita ko yung bagong curriculum ng DepEd, nag-include na sila ng nuclear physics. So, at least para pagdating nyo sa field, alam nyo kung ano yung content ng nuclear physics. Kung paano nga ba, ano yung radiation, ano yung radioactivity, ano yung alpha decay, mga beta decay, mga ganyan. So again, itong discussion na to is connected sa astronomy. So hindi ko na po uulitin ito sa subject natin na astronomy. Doon nakalagay sa syllabus itong topic na ito. Okay? So again, you can watch this one during your free time. Lalo't medyo, sabi natin, yung schedule natin ng June ay pabago-bago at maraming ganap. So I hope na makatulong ito para at least makover natin yung mga topics na i-discuss dapat natin sa ating subject na modern physics. So with that, maraming salamat po sa manonood ng ating synchronous video na ito. So okay, goodbye class. Thank you.